Right, let's get started. So today, um, it's going to be sort of a continuation of the heterogeneous computing series that we've been doing. And today is actually an interesting one. So I happened to come across this new repo. It's called CubeCL. It's by the folks who are working on Burn, which is uh, basically a machine learning framework uh, written completely in Rust. Um, so one of the things that when you do get started working with machine learning in Rust, you end up noticing that um, you could probably write a framework that is write your models or work with your models essentially in Rust. But when it comes down to actually getting you know basically doing the acceleration part of it, that is, you want to offload some of the compute to your GPUs. I don't think there's no support for accelerators, but yeah, just GPUs. You'd end up, in a different world. You'd actually have to, uh, you know, reach into whatever the GPU vendor offers. In CUDA's case, that's CUDA. In the case of Apple, that's Metal, etc. Or you could sort of, go a different way and use, uh, you can use frameworks that are sort of providing an abstraction over these vendor provided, uh, layers, like for example, OpenCL, etc. And there's also WebGPU, which is something that I've discussed in the past. So I'm not going to talk about that here, but note that, you've got uh, your vendor-specific SDKs or APIs that are provided to you. They could be compute APIs or rendering APIs, but those APIs like Metal in the case of Apple, DirectX 12 in the case of Windows, and then Linux, it's Vulkan. All of these particular APIs, they've actually layered on top of that web GPU so that you have like a common cross-platform API that you can use. CubeCL, on the other hand, is a little different. It's the idea is you basically take away the need to write your, you know, let's just if you're talking about GPUs, you focus on just writing everything in Rust, including your GPU kernels, and that's kind of what that's the first thing, which is what I guess the title or the tagline says: multi-platform high performance compute language extension for Rust. In other words, you could basically write, GPU kernels in Rust. That's the coolest thing about this project. This is something that I've been working towards. The fact that there's already somebody who's put together a project, it's a great thing, and I want to delve into it. This is the first time I've actually come across something like this. Um, so I started looking at some of these things. It's as simple as, annotating your Rust functions with, basically a simple macro, a procedural macro in this case. Obviously, you'll have to delve into the, what's going on over there. Um, and then I also noticed that, somewhere down here, I just read this, that they happen to be using their own IR. Where is that? Because most of the time when you're working with something like GPU kernels, etc., it's not that you can't write stuff in Rust. It's that you really need to take your programming model and map it to the execution model. And the programming model and the execution model are slightly different from what you find in the CPU world, um, especially the GPU side of things. You have things like warps. If you take the case of NVIDIA, you have threads, obviously, uh, but you have things like warps, and you need to schedule warps and all of that. So that's the programming model. And the hardware itself is very different, because you could always draw comparisons between something like CubeCL and, let's say, vector instructions on your CPU. But that's I think we discussed this as well, so I'm not going to jump into that. And plus, I just wanted this to be quick because I just saw this. It's been about 30 minutes, I guess. It's very, very interesting. So I thought I'll quickly just, you know, uh, for my own sake, when I come back to it, because I do have a bunch of projects that I remember what I was talking about, and B, in case it proves to be helpful to somebody who happens to again land on this project. Great. So without wasting much time, so you basically annotate your Rust functions with these two proc macros, I guess. One's called launch unchecked, and one doesn't have any, check. I presume this is a safer one. So I'm guessing, obviously. So let's actually do this. Mm, mm, Where is my thing? Okay. So this is the examples. So let me look at that here. And is that right? It's the same thing. So interesting. But yeah, rather than this, let's just go ahead and do what we do best. I'll just expand the crate macros. So I get this. So this is a little trick that you can use if you're dealing with macros that you're seeing for the first time and you don't want to deal with jumping into them and trying to figure out what the hell they do. That is, what do they expand to? So my suggestion would be simply do this and go ahead and copy paste that. Now, obviously, I guess you're going to run into some warnings, stuff like that. And then you run into some errors. Great, even better. Just like that. Yeah, you could just simply do this. So when you write proc macros, you're going to leverage things like unstable features, etc. So that is a thing. All you do is you just, you know, get this to work by so we go back here. All right. So that should compile now. Great. Now, so if you do that, what's easy is you can actually see what does that macro expand to. So the original macro was this, like you got a Jalu array, and then you got this, and then you had like a, you know, uh, so if I was to just go in here and do uh, examples, Jalu, and look at the source, you'd see that, yeah, this is it. So this is what we had, this is what, and it expands to this. So you basically have a module where you have a Jalu array struct, then it implements the kernel. What is the kernel? Yeah, I'm guessing that, this is our kernel. So there's a way to properly, identify that as a kernel when we implement the kernel trait, which is basically, yeah, that's what I think it is. You define, convert to a kernel definition and identifier for the kernel used for caching kernel compilation. But so that's fine. Um, and then, yeah, this is the full expansion. Okay. And then there is a launch unchecked function that's going to be also part of the expansion. And yeah, oh, this looks like it. There's an expansion as well as happening. Oh, wait. So this stuff is actually going to expand into some other intermediate representation. That's what it looks like. All right. They're using a Rust function for that. That makes sense. Interesting. Okay. So where is the IR then? Yeah, that's it. That's the IR. But is there any documentation for it? I guess not. Okay. This is going to take some time. Let's not waste time over there. Hmm. There's a front end as well. Okay, let's go back and see this. So you annotate the functions with the cube attribute to indicate that they should run on the GPU. That makes sense. You then launch the kernel using the auto-generated Jeru array launch unchecked. We just saw that that's what this is where that. Wait, only done that and that. Yeah, that's what this is. Launch the kernel on the given runtime. I'm presuming the runtime over here is what? Yeah, the runtimes of these. That's it. So it supports WebGPU and CUDA. That's really good actually, because WebGPU is the is the abstraction that a lot of a lot of the you know players have actually put their weight behind. That's the Apples, the Googles, the Microsofts, all of them. They seem to be adopting WebGPU, so that's a good target to go for. Uh, yeah, so I think there is a plan for Metal and Rockham and Vulkan and all that. Great. We also plan to develop and optimize JIT CPU runtime. Ah, that's good. That's good. So I was wondering whether there's a fallback. If you don't have any of this stuff, or if you don't want to use any of this stuff, can we simply just use SIMD instructions? Because in some cases, it's just better. Um, you don't have to deal with threads and synchronization and all that overhead. SIMD instructions are basically a single sequence of instructions that use vector registers and a vector length. I think we've discussed that, so it's good. Uh, and if I was to look at this, okay, this is how we launch. Let me just. So if we just, I've actually run this, so I'll just show you what you can do. Uh, where is that? Yeah, so I want to run it with the web GPU thing. So I'll just run this particular example with the web GPU thing, and you should be able to see some errors because I did run it before. Uh, and if you go back to the actual example, you see that, you know, uh, yeah, you see that this is the input that was provided, and the output is something like this. Yeah, that's close by. And this should be this. Okay, it's not exactly that because this stuff can change depending on precision, floating point precision, etc. But that's fine. So that makes sense. All right, the thing that I don't see here is you got the runtime, you're able to annotate them, we're able to expand that into this. Obviously, there's a register inputs and stuff like that. So probably need to figure out what this is out. What is this? Yeah, this is the thing. When you expand a macro and you try to look at it, you're like, whoa. So you should be able to take that macro, the expanded output, and then sort of replace whatever was the previous, macro version with the expanded macro version. You should be able to get all this beautiful documentation. And defines how a launch argument can be expanded. Oh yeah, I'm pretty sure there is. This is going to convert into some IR, but what is an example of what the IR looks like? Maybe the goal of CPI, yeah, this part. This is just fine. If you want to write highly optimized compute kernels that will run across hardware, so that's great. You either have Yeah, this is exactly what you do. You either have to write custom kernels for different hardware, often with different languages like CUDA, Metal Rock, and etc., or you just use theirs exactly. So we created a just-in-time compiler with three core features: automatic vectorization, Comptime. What is this? The Comptime? So auto tuning, yeah, automatic vectorization. So automatic vectorization is so basically you're given a piece of code and you you've not specifically explicitly stated that this is going to you need to run this code through, if it's a CPU, through the vector hardware, or if it's a GPU, you want to actually leverage the the parallelism that it offers. What happens over here is the compiler can do this for you. It can detect certain you know things in your code path, I guess, and then figure out whether this can be vectorized or should not be vectorized. That's automatic vectorization. Auto tuning is the holy grail of what pretty much every deep learning compiler is trying to do, because depending on which kind of input you're providing, some kernels might be better at it. So the same, you might have one kernel, which is probably matrix multiplication. Let's take that. But you can have different versions of matrix multiplication depending on your inputs. So that the precise input shapes and other configuration parameters will it turns out that you get the best possible performance. So one single implementation may not necessarily be the best way of getting the every drop of performance. You might have several variants of it. And auto tuning is a way to actually sort of benchmark that. That means you run your kernel with different uh, configuration parameters, and then you see which one gives you the best result in terms of purely in terms of performance. And then you basically pick that and say that this is the best, kernel for exactly this particular kind of workload. Um, so that's good. They improve code composability, reusability, and testability. Well, I'm definitely sure for reusability and maintainability because you just have to learn one language, which is Rust. And in this case, that's the best part. Uh, let's look at composability and testability. I don't know. We'll see. CubeCL also ships with a memory management strategy. All right. Okay. Our goal extends beyond providing an optimized compute language. We aim to develop. Oh, great. Very, very nice. High performance and computing and scientific computing. I think that's what Rust badly needs right now. There's a lot of work that you can pretty much find a crate for something that you do want to do on the CPU. You also have a SIMD, addition to the standard library itself, I guess. Uh, that's all CPU stuff. But the moment you step out of the moment you move away from the CPU, you're like, okay, I have to learn a new language or I have to learn a new thing to get some work done. And I think that's very, very interesting. Hmm. To achieve this, we are developing linear algebra components. Okay. Mhm. Okay, so that's what I think I made a note of this here. That's what they mean, right? By the way. Instruction specialization, which is what this is, right? You can use tensor cores, which probably mean specialized instructions as well. And the number generation. Okay. The small team. Oh yeah, absolutely. From what I see right now, I certainly want to, you know, figure this out and see how I can help. This is cool. Yeah, this is what we just saw. So you parse and you expand, use a sync rate. It's not much there. Yep, if you're using an intermediate representation, and the generated function semantically similar to the original one is responsible for creating the IR when called. This approach differs from traditional compilers. So basically, the project is a compiler. You have a just-in-time compiler that they've built. So you take your Rust, code, you produce some IR, and then you do your optimizations on the IR, like things like automatic vectorization, etc., etc. And then you probably target your backends, which is web GPU and CUDA, right? Mhm. Okay, interesting, interesting. This is what I mentioned when I talked about programming model versus execution model. Pretty much it's very similar to, you know, if you think of CUDA or uh, Metal or any of them. So thread groups, warps, wavefronts, everything, the same thing. Topology, yeah, it's exactly the same. Okay, so this is a grid dimension. It's called cube count. Block is called cube position. It might be a bit difficult if we're coming from these other places because this looks very different. Okay. Yeah, I think we saw automatic vectorization, etc. And this is Comptime. So I guess these are the five things that I was looking at this. Mm, And auto tuning. Great, great. Mhm. So CubeCL isn't a new compute language, though it feels like you're writing GPU kernels. You're in fact writing compiler plugins. Exactly what I thought. You can fully customize. Comptime is a way to modify the compiler IR at runtime when compiling a kernel for the first time. So you can do all of this stuff right now at compile time. I love the fact that we stole Comptime from Zig. It's interesting. Yeah. But this is not the same thing as Zig, I get pretty sure. Uh, all right, so this is interesting. What I want to see is, if okay, wait, I saw something here. Ask on Discord. I also saw linear algebra, so let's go take a look at that. Oh, there's another example. So you got tiling 2D matrix multiplication. I've already done uh, a stream on that, specifically using the Metal API, and that's using Metal RS. So you should be able to find that video. And let me see if I can just quickly just point to that. Yeah, so here's it. So this is the one that this is when I first got started with GPU computing a little bit, and figured I'd go look at how this works. So MapMeld implementation that uses tiling is something that I did implement. And if you actually looked at it, what's happening here is if you go look at the source, there's the main stuff, which this is the stuff that you write in Rust, right? This is the stuff that you write in Rust. But the moment you want to actually offload some compute, like you want to take, a million rows of a million elements in a matrix, multiply that with another million element matrix, which is a pretty big, multiplication. You pretty much have to reach into something like this. And then you would write, a matmul shader, which is the compute kernel or a GPU kernel that actually runs on the GPU. This is all C++. You can see this is not really something that you want to break your head on because you start to get into templates and you know, a lot of the C++ stuff that you don't want to be doing comes up here. Anyway, I'm just very glad that when we can now do this, we can simply just do with that. Let me go back. This is the documentation for Cubicle. Yep. So you can just do this, and then you should be done. That's cool, actually. Okay, so I need to jump into more of this, understand how the IR is built. So I'm pretty sure I understand at least some parts of the layout of this crate. So you've got cubic core, which I guess contains more of the core types. Yeah. Your code generation. The front end, my understanding of the front end so far is that Rust is basically a front end. I think I read that here. Hmm. Okay, where did I read that? Yeah, right. Okay, so here they say this. The project is started out as a web GPU only backend for Burn. As we optimized it, we realized that we needed an intermediate representation that would be optimized, that could be optimized, then compiled to WGSL. Having an IR made it easy to support another compilation target, like CUDA. However, writing kernels directly in that IR wasn't easy. So we created Rust frontend using the syncret, navigating the differences between CUDA and WebGPU while leveraging both platforms forced us to come up with general concept that worked everywhere. So very interesting. I mean, I'm something very similar. I was tweaking, fiddling around a bit with MLIR and LLVM, trying to do something very similar. I didn't get very far though because I didn't have a lot of time and just, you know, too much work and too many pieces. The fact that, this is already in some shape or form ready and it's actually working, it's very, very interesting. Okay, so what I don't see is I was looking at the documentation to see if there's an example of what their IR looks like. Uh, okay, that I guess I can figure that out, but we'll see. Anyway, this is basically me just, exploring this as we go along. So I'll figure it out. Anyway, that's about it for today. Thank you.